Hi, everyone. So, what we're going to do today is you're going to learn a shortcut for derivatives. Now, you've already learned the definition of derivative, right? F of a plus h minus f of a over h as h approaches 0. Well, we have a shortcut. And the shortcut we're going to talk about is called the power rule, which basically says if you're going to derive a function, you take the exponent and multiply it with the coefficient of that term, and then subtract 1 from the existing exponent. So the easiest way to learn this is to do a couple of examples. So let's go ahead and do that. So here we go. So to take the derivative of 4x to the fifth, first of all, we'll write the derivative f prime of x equals, we say 5 times 4 is 20 times x to the, 5 minus 1 is 4. And that is the derivative. Okay, let's do another one. So we have to find f prime of x of 3x squared. So 2 times 3 is 6. X to the 2 minus 1 is 1. It's as simple as that. Here we go. Now we just have an x. So you might want to think of this as having a 1 here and having a 1 here. So 1 times 1 is 1. X to the 0, well, we don't write x to the 0. We know anything to the 0 is 1. So we just get 1. For an example like number 6, what we typically do, and this is where we're going to get into some things that you're going to have to think about. We typically would say x to the third, let's bring it to the numerator, and we write it as 5x to the negative third power. Now we can easily take our derivative. We say, well, negative 3 times 5 is negative 15. X to the, negative 3 minus 1 is negative 4. And to be honest, a lot of times we just leave it like this. Sometimes you're going to rewrite it so that you bring that x to the negative 4 into the denominator and make it x to the fourth. So we'll get into that a little bit later about when to move things around, when to just leave it. So that's the basics, okay? That's the main rule here, the power rule. What we're also going to be talking about are a couple of kind of specific cases for the power rule and how things, sometimes turn out a little different, things for you to think about. So let's take a look first at the derivative of a constant. Well, if you think about it, if you take the derivative of just a number, I'm going to actually give you the example and then the rule. If I told you to find the derivative of this function, well, we have x to the 0 here kind of as an understood value, right? So 0 times 5 is 0. And even if you put times x to the negative 1, it would still clean up to be 0. So the derivative of a constant is 0. So the derivative of any number that doesn't have a variable attached to it will be 0. The second one, I don't really use too much, but if you wanted to, if we were taking the derivative of a constant times a value, what we could actually do is kind of pull that out in front and then take the derivative of what was left. So an example of this would look something like this. Take the derivative of 3x squared. So what we can do, now we know the power rule, so that's why I said we probably won't use this too much. But what we could do is we could take the 3 out in front and then take the derivative of x squared. Okay, now this is multiply. So what is the derivative of x squared? Well, we know now it's going to be 2x to the first. And now we'll simply multiply these to give us 6x. To be honest, I just think it's easier to do the power rule. Okay. And the sum and difference we've actually it's going to be very simple. What we're basically saying is if you're deriving a function that has multiple terms, essentially derive each and every term and then either add or subtract them. Okay, so the example here would be if we wanted to find the derivative of, let's see here, if we wanted to find the derivative of 2x cubed plus 4x squared. Okay, we'll just take the derivative of 2x cubed. So we'll use our power rule. 3 times 2 is 6 times x to the second power plus derive now 4x squared. 2 times 4 is 8 times x to the first power. So we just simply took the derivative of the first term times the derivative, plus the derivative of the second term. Okay? So let's see what we have here. We have a couple of more examples using these rules. And again, power rule is going to be the best way. On letter D, you're probably going to want to rewrite that one. So let's take a look at this. Enlarge it a little bit. Okay, so the first one, well, the derivative of any constant, I don't see a variable there. So the derivative is simply 0. For letter B, we have the derivative of two terms being added together. So you're simply going to take the derivative of the first term. 2 times negative 5 is negative 10 x to the first. And then the derivative of 3x is just 3. And remember, x to the 0 is just 1, so we don't write that. For example C, we're going to use power rule. Okay, we're going to have to think about this as kind of combining a couple of things. So the derivative of 2x cubed, say 3 times 2 is 6, x to the second power, and then the derivative of a constant is 0. So that's it, 6x squared. The last example, what I would do is I would rewrite this middle term. So I would keep 3x to the fourth, but I would remember this is x to the 1/2, and then I would bring it up to the numerator. So we'll have minus 2 times x to the 1/2 plus 8. When we express our radicals with rational exponents, it's much easier to derive. So let's take the derivative using what I just wrote over there in purple. So we have 4 times 3 is 12, x to the third, minus 1/2 times 2 is 1. I'll put that there for now. X to the, now you have to think about this. It's 1/2 minus 1. Maybe you like to think of it as 1/2 minus 2 over 2. Doesn't matter. However you do it, you should get x to the negative 1/2. And then, of course, the derivative of a constant is 0. Again, many times we will just leave this as it is. There are some times where we will move the negative exponent to the denominator. So we would have minus 1 over x to the 1/2. So it just depends on the problem. And to be honest, it's, I don't have a preference right now because we're not really using these. Okay, so you have many, 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 many examples here. I would like for you to do, oh my goodness, I would like for you to do all of the problems up to here. Okay, you're going to pause this video. You're going to do all of those problems and then check against my answers. And then we'll do maybe a few together and then I'll set you free. You can do a couple on your own. Okay, so pause this video. Try to take these derivatives. You got this. Okay, so take a look at these values. Okay, see if your numbers or your values for your derivatives match up with mine. A couple things you might notice is I did a couple of rewrites. For example, this one right here, as I told you on the previous page, you're going to want to bring that x to the third up to the numerator and make it x to the negative third. Okay, same thing here. We're taking that x and bringing it to the numerator to make it x to the negative 1. And these last two were both in terms of radicals, and it's easier. We want to rewrite those as x to the 1/2 using their rational exponents instead of the radicals. So once you feel pretty good about those, okay, we're going to go ahead, and I thought maybe I would do this first radical one with you and a couple of others too that I'm going to kind of just pick here and there. So let's take a look at this first one, and what I would recommend is rewriting it as x to the 7/4. So now when we take the derivative, we have 7/4 times 1, which is 7/4, x to the, and now we do 7/4 minus 4/4, which gives us x to the 3/4. So you definitely want to rewrite that radical with a rational exponent. For the next two in line here, you're going to want to bring that up to the numerator. So we know this is x to the 1/2. When you bring it to the numerator, it will be x to the negative 1/2. Same thing here. Now be careful because yes, this is 4x to the 1/2. You do not bring the 4 up there. The 4 does not move. You bring just the variable with its exponent and make it like this. And you might want to put that 1 there. Okay, so be careful with that one. This one right here, I highly recommend when you can reduce at the beginning that you do that. Here is the reason why. We have x to the first over x to the 1/2. Well, we know we can reduce this. 1 minus 1/2 simplifies this to just be x to the 1/2. And that is what you will take the derivative of. So I'm going to set you loose again. Stop the video. Go ahead and take these derivatives and then check back in and see if yours match what I get. Okay, take a look. Check out your answers, see if they match mine. Tried to show you how I rewrote things, okay? Some rational radicals that I turned into rational exponents that definitely make it easier. So take a look at these. And we look now, we just have two more that didn't fit. So you should be able to do these, but I'll go ahead and work through them with you, okay? Just in case you need a little clarification. So what I would do for this one is I would simply do a rewrite, thinking that this is x to the 1/2. I would definitely bring that to the numerator. So we'd have 2x plus 4 times x to the negative 1/2. So now when we go ahead and take the derivative, well, the derivative of 2x is just 2. And then we have negative 1/2 times 4, which is negative 2x to the, we're going to subtract 1 here. And again, you might be thinking of it as minus 2/2. So we get an exponent of negative 3/2. Okay, for the next one, I would definitely think of this as x to the 1/3, and then I would look to clean this up. So I would do a rewrite that would say 4x cubed minus 5. So x to the first minus 1/3 gives us x to the 2/3 in our numerator. And that is what we will take the derivative of. So when we take the derivative of the first term, we get 12x squared. So we have 12x squared minus 5 times 2/3. So we'll get 10/3 x to the, and now we have 2/3 minus 3/3, which is negative 1/3. Okay, so great job today, everybody. Have a good day.